Okay. So let's continue on with section 4.5. We're going to be solving all kinds of exponential equations, logarithmic equations, and we'll see just whatever it takes to do that. So let's solve this thing. Try this one out for size. That's 1.11 raised to the xth power. Bring it up here a little bit. And so, of course, since we are solving this equation, what we want to do is we want to get x by itself. We want to isolate it. We're figuring out what value of x can be substituted in to create a true statement. Well, usually the protocol is going to involve you getting the statement with x kind of by itself as much as possible. So the first thing I'm going to do here, I'm going to subtract this 1 from both sides, leaving me with this. Equals 13 now. Then I'm going to divide both sides by 4. Leaving me with 1.11 to the x equals 13 over 4. Now we can actually, dividing by 4 is not very perilous, so we can actually write that as the decimal number 3.25 if we want. That'll probably help us. Now, we notice that we're raising to the xth power. We need to get x out of the exponent so we can actually do stuff with it. So we can actually kind of solve for it. So what we're going to do, we're going to need to take a logarithm of both sides. Technically, you can take a logarithm with any base that you want, but let's take a logarithm with a base that we can find in our calculator. So we're going to take the natural log of both sides. So I'm going to take the ln of the left-hand side and the natural log of the right-hand side. And because of done that, the x here is going to, thanks to the power rule of logarithms, come down here to the front. So I'm going to end up with x times the natural log of 1.11 equals the natural log of 3.25. And now the natural log of 1.11 is just some number. The natural log of 3.25 is just some number. So I'm going to divide this thing over to the other side. Divide both sides by the natural log of 1.11. And so what I'm going to end up with, natural log of 3.25 divided by natural log of 1.11. Now we need to use our calculator. We do ln of 3.25 divided by ln of 1.11. And you can write exactly like how you see it here into the calculator. And when you do that and you round to 3 decimal points, you should get 11.294. There you go. That will give you what you want. And so that, make sure whenever you're on the exam, you pay close attention to however many decimal points it wants you to round to. That's going to be kind of the key here. Okay. Let's try out another one. And that's really all we're doing today is we're going to just be working a lot of problems. These are problems over section 4.5, which is covered on your exam. And then we will work some review problems for some other sections. So this next one is going to be five e to the 2x plus 4e to the x it's going to equal 12. There are people waiting to get in. Thank you. It did not pop up on my screen. Okay. So whenever we look at this one, we're tempted. This is going to be a nice tricky one. We are tempted to try and take the natural log of both sides.
Can you hear me?
Yeah.
There's a couple of people that are in the waiting room that you need to let in, I guess.
Yeah, I let one person in. I don't see anyone else in there.
Okay. Good. I don't know. Thanks.
Yeah, I was able to let JC in. But I do not see anyone else in the waiting room. So, we're tempted to take the natural log of both sides. The problem is if we took the natural log of the left-hand side, that's actually not going to help us because there's addition going on inside the logarithm. We don't have any special rules for that. We have no special magical rules that allow us to deal with the addition on the inside. So bottom line is, but it won't help us here. Okay, so back to the drawing board. It turns out that there's something really wicked we can do with this one. And it's not something you might immediately think to do, but that's why we're working it together. what I'm going to do is I'm going to rewrite this like that. Exponential laws say that I can rewrite it like this. This x and this 2 would just get multiplied together. Why would we do that? Because we're going to recognize this as being in quadratic form. We're going to recognize this as being in quadratic form, which really means we can rewrite it as a quadratic equation. Let's see, someone wrote in the chat wrong. And so what we can then say if we write it like that, that's really going to kind of drive that point home. Because to make a substitution, we're going to say that y is equal to e to the x. Just like we did back in, I think, chapter 2, when we were solving equations that had a quadratic form to them. And the reason we can, or what's going to happen when we do that, is now this is going to just become 5y squared plus 4y equals 12. So that's the leap that we want to make here. That's what's going to help us put this equation down. And now we just need to solve a quadratic equation. So solving a quadratic, we want to get everything on the same side. So we're going to move the 12 over. Now, there's a couple ways we can handle solving this quadratic. We can hope that we can factor this thing. And if we can factor it, that's going to make our life easier. Another thing to note is that we're going to have a couple screens we might have to take up here. So I might have to, excuse me, delete everything above here in order to solve this one. So let's go ahead and do that. But I'm going to leave the substitution we made on the board. So let's see how we'll do that. Leave the substitution up here. I'm going to delete all this. Maybe we can try factoring it. Now remember, whenever you're factoring and there's a value in front of the squared term, what you do is you do 5 times negative 12, which will give you negative 60. And now what you're looking for two numbers that have this property, that whenever I multiply the numbers together, I get negative 60. So we're looking for factors of negative 60 that when added together give me positive 4. And it looks like there will be two factors that do that. It looks like it'll be 10 and negative 6 will do that. 10 and negative 6. So I'm going to split up this middle term. I'm going to call this 5y squared plus 10y minus 6y minus 12 equals 0. And now, whenever I do that, now I'm going to factor by grouping. I'm going to look at this as group 1. I'm going to look at this as group 2. I'm going to take the greatest common factor out of each group. So from group 1, that's going to be, looks like 5 times y, 5y. Leaving me with y plus 2. In group 2 here, I'm going to factor out a negative 6. And in doing so, that's going to flip the signs here. I suppose I should put this in red. Then I'm going to factor out a y plus 2 altogether. So I'm going to end up with y plus 2, and I'm going to be left with 5y minus 6 equals 0. Then I solve each. Remember, I set each factor equal to 0. And there I add the 6 over, divide by 5. Now, normally I would be done here. Normally I'd say, oh, well, I just solved a quadratic, so I'm done. Well, not so fast. Again, this problem takes up a couple screens. Not so fast. We got it down to this. To these y values, but now there's a fly in the ointment because remember, y was equal to e to the x. We actually made a substitution way back when in order to put this into a simple quadratic form and solve a simple quadratic. So now we kind of have to stick to our guns here, and now we have to basically undo the substitution. And now since y is equal to the e to the x, we're going to put e to the x back in for y. And so now our variable x is in the exponent, but that's going to be really easy to remedy. If you want, you could take the natural log of both sides, or you can rewrite each in logarithmic form. So remember, rewriting a logarithm out of an exponential, it's going to be log base e of negative 2 equals x, aka ln of negative 2 equals x. Because the log base e is just the natural log. Wait a minute, this is actually going to be a problem here, but we'll deal with it in just a second. Let's rewrite this into exponential form. It'll be the log base e of 6/5 equals x, or ln of 6/5 equals x. So if we look at each of these, this one has a huge problem because a logarithm can't take in a negative value as an argument. That's not allowed. So actually what that does is that completely wipes out this one and says, nope, not going to happen. But the other one's going to be okay. X equals the ln of 6/5. That one's okay. And that's going to be our answer here. The natural log of 6/5. And if you wanted, you can get that out to a couple decimal points. If that's what your heart is set on, about 0.182. If you round to 3 decimal places. So that one's a tough one. That one's not an easy problem to solve by any means. But we did it. We just took it step by step. Rewriting it in the quadratic form was kind of the key that cracked the whole thing open. And so, unfortunately, just like in general equation solving, there's no one blueprint that works perfectly for every equation and always solves it. So that's just what we're going to have to keep in mind. Some of these, each of them is going to require a different approach. Kind of the more math we understand and the more experience we have, the better equipped we're going to be to actually solve different types of equations you might see in the wild. So that one was a particularly tough one. This next one actually is not going to be all that tough. So again, we're still trying to solve. Log base 6 of 6x minus 7 equals 4. So we look at that one. There's a few nice things about it. For one, our x value is in the argument of the logarithm. And then the 4, if we were to rewrite this in exponential form, the 4 would be the exponent on a 6, meaning that x would not be in the exponent. So it may actually make sense for us to rewrite in exponential form. That might actually make perfect sense for us. So rewriting in exponential form, that's going to be 6 to the 4th equals 6x minus 7. And now what we'll see is this one's going to go easily. This one's going to actually be pretty easy because all we got to do is figure out what 6 to the 4th power is. It's just going to be a number, and then it's just a simple linear equation to solve. Okay, so 6 to the 4th, you have your calculators. You can use those calculators. 6 to the 4th is going to be 1296 equals 6x minus 7. And now we just solve this like we would any simple linear equation, one variable linear equation. So that's going to give you Well, 1296 plus 7 will be 1303 equals 6x. Now divide both sides by 6. We'll get 1303 divided by 6 equals x. And that's literally the answer. And that's not so bad. Of course, if the problem wants you to evaluate that and round it to 3 decimals, it would be 217.167. Again, you can use a calculator to do that. If the problem wants you to leave it in exact form, you'd literally write the fraction 1303 over 6. So that's one possible thing you might be asked to do. You might be asked to solve something that looks like that. And in this case, the solution came if we just rewrote it into exponential form. Let's try yet another one. Well, these are good problems to work. These are popular types of problems to use on an exam. Log base 12 of x minus 2 minus log base 12 of x plus 7 equals log base 12 of 3. So we're going to try solving this one. Now, one thing I'm going to note, logarithms are very particular. Remember, logarithms will not let you take in a negative number as an argument. They also cannot produce a negative number. So logarithms are very particular. So going forward, we need to check our solutions against the original equation to make sure they're logical. In other words, we're going to solve this. And just like when we were solving certain equations earlier in this semester, what we need to do is whatever value we get for x, we need to plug it back in to the original equation and make sure that it makes sense. Make sure that it's not something just out of the ordinary or incorrect. So we're going to end up needing to check our answer here. So just keep that in mind. Now we look at this, and I kind of don't like this left-hand side because I'm subtracting one logarithm from the other. So my first step is going to be, I'm going to combine the left-hand side. I'm going to condense it into log base 12 of x minus 2 over x plus 7. You'll remember that was the quotient rule for logarithms. I'm subtracting one logarithm from another that both have the same base, in this case, of 12. And so they can condense into a single logarithm where we divide the first argument by the second argument. And then the right-hand side, didn't change. It's just still going to be log base 12 of 3. Now, one thing we can note, we have a logarithm with a base of 12 on both sides of the equation. So each side of the equation is a logarithm, a single logarithm with a base of 12. The only way that this left-hand side is going to be equal to this right-hand side, the only way they'll be equal is if their arguments are equal. You're taking the log base 12 of something, you're setting it equal to the log base 12 of something. The only way that each side of the equation will be equal is if the somethings are equal, is if the insides are equal. So we're going to make this leap here. So in other words, we can just equate their insides. And now we look at this, there's a couple ways we can solve this one. I think the best way is going to be to take this denominator and we're going to multiply both sides by it. So I'm going to multiply by x plus 7. I'm going to multiply this side by x plus 7. It's going to cross them out over here. I'm going to be left with x minus 2 equals 3 times x plus 7. Now I got to clear some room here. We're down to here at this point. What I'm going to do, now we're just solving for x. There's no logarithms involved anymore at the moment. This is just solving a simple one variable linear equation. I'm going to distribute this 3 so that everything gets on the same playing field. So 3x minus 2 equals 3x plus 21. There's a couple things we can do here. We can add 2 to both sides. We're going to be left with x equals 3x plus 23. Then we can subtract 3x from both sides. Trying to get x by itself. Negative 2x equals 23. Divide both sides by negative 2. You'll end up with x equals negative 23 halves, or negative 11.5. So you want to say, you're tempted to say that the solution is negative 11.5. You're so tempted. That's the only possible thing it could be, but it's not guaranteed to work. Because now look at this negative 11.5. If we were to go back and plug it all the way back into the original equation, you plug a negative 11.5 in here, you're going to end up with a negative value inside the logarithm. And even same if you do here, negative 11.5 plus 7 is still negative. So you're trying to plug a negative value into the logarithm. That, my friends, is not going to work. That's going to create some problems. So we're going to check our answer. You're going to end up with this thing will end up being a negative number, which is a problem. You can't have a negative argument to your logarithm. We covered that the other week when we first started talking about logarithms. Which means that this is not allowed. That's not a solution that's going to work. And so finally, we're going to say there's no solution here. That is the true blue bona fide answer to this problem. No solution. On your homework, they might word it a little differently. They might say the solution is the empty set. It's the set that contains nothing in it. They'll usually use this symbol to represent that. And that's the same exact thing as saying that there's no solution at all. Whoops. Let's see. So pretty interesting problems we're facing. It's kind of good that we are getting a lot of different problems. We generally want to see as many different kinds of problems as we can. The last one will work will be an interesting finance problem. So the last one will work from this section is something involving money. Now, as a lot of you know, it's generally very wise to be smart with your money. A few very simple financial principles I can give you right now. If you can, avoid credit cards as much as possible. Because credit cards can create a situation where, oops, stop sharing, go back. Credit cards can create a bad situation where you try to spend more money in a given month than what you actually make. And that means you're going into debt in order to finance that. And then credit cards have ridiculous interest rates on them that are just, they gouge you. They're very, very predatory. Most credit cards can have up to a 25% interest rate, which doesn't sound horrible. It's horrible. The 25% interest rate is just absolutely just highway robbery almost. What that means is that if you start off the year and you owe $1,000 on the credit card, after 1 year, you're going to owe about $1,250. But the problem is if you don't make your payments and get rid of that debt and pay it off, it's only going to get worse and worse. After 10 years, I mean, you could owe 5 times as much as what you started with, maybe even more. So it's important to understand the basics of interest and credit card debt. So what we're going to do is we're going to use a special formula. And this is the formula that's given to you in your textbook. And we won't go into uber detail about it, but I will define what these variables are. This is the formula for compound interest for a lump sum, that is a single amount of money. You can use this formula to basically compute, hey, how much money will I have in an account if I put this much away right now for a number of years, for 6 years, 7 years, 10 years, something like that? How much money will I end up with in the account? Here's what the variables represent. A is going to be the accumulated or future value. It's going to be how much total money you have in the account after so much time. P is going to be the principal or present value. It's going to be how much is in the account at the beginning. R is going to be the interest rate expressed as a decimal. K is going to be weird. It's going to be the number of times interest compounds each year. T is going to be the number of years. So A, P, R, K, and T. Most textbooks use N instead of K. I don't know why they're using K here. So let's work a problem, and I'll show you exactly how this formula works. How much time will be needed for $37,000 to grow into, let me give you this amount of money, $39,279. $39,279.16 if deposited at 3% interest compounded quarterly. Okay, so kind of an interesting problem here. What we're going to do is we're going to use this formula. This formula kind of rules over this problem. It determines everything for us. And what I'm going to do is I'm going to write out what each of the values are for this problem. And any value I don't know, I'm going to leave it unwritten, and that's going to be what I'm solving for. So the accumulated or future value, what I'm doing in this problem is I'm putting $37,000 into an account. Now, most of us would probably be very happy to have $37,000, but I'm going to put it into an account, and I'm going to save that money. And I'm going to save it. It's going to get 3% interest, which is kind of hard to exactly tell you what that means. But basically, if it was purely 3% interest, then that means every year it's going to be 3% larger than it was the year before. Then it's going to be compounded quarterly, which we won't talk too much about what that means. It simply means that instead of waiting till the end of every year to get some of my interest, instead I only have to wait till the end of every quarter or every 3 months in order to get a piece of my yearly interest. And what this problem wants to know is how long will it take for $37,000 to grow into $39,279.16 at all these other factors. So the accumulated or future value is going to be $39,279.16. The present value is going to be $37,000. That's how much I'm putting away at the get-go at time 0. My interest rate is going to be 3%, which we're going to express as 0.03. The number of times interest compounds each year, that's going to be my K value. That's going to be K, and that's going to be 4 because interest is compounding quarterly. Finally, T is the unknown variable. It's the one that gets the big question mark. Okay, so we've got everything we need. We're just going to plug these values straight up into the equation, and then we're going to solve for whichever one we don't know. So since T is the question mark, I'm going to leave it as a T in the equation. So I'm going to plug everything in. It's going to be $39,279.16 equals 37,000 times 1 plus 0.03 over 4 raised to the 4 times T power. And now we are most certainly going to run out of room, so I'm going to have to erase all this above now that we've already got it all into the equation. I have to give myself a little more space. Oops. Now, look where my variable is. It is in the exponent here. So unfortunately, I may have to use a logarithm. In fact, I'm definitely going to have to use a logarithm in order to solve this. Now, a few other notes. You can use your calculator. You can certainly use your calculator. I'm going to do 0.03 over 4. I'm going to do that because that's not going to be anything too horribly wild. It's going to be 0.0075. So this right here is going to be 0.0075. So now this inside, if I add that to 1, is going to be 1.0075 to the 4t. I have everything else around it. $279.16 equals 37,000. Next up, I'm going to divide both sides by 37,000. This side as well. So we have $39,279.16 divided by 37,000. That's going to be equal to 1.0075 to the 4t power. And now what I can do is I can take a logarithm of both sides. The reason to do that is because my variable is up here in the exponent, and that's going to allow me to take it out of the exponent. So I'm going to have ln of 39,279.16 divided by 37,000 excuse me, equals the ln of this business. And because I took a logarithm, I can bring down my 4t here. So I'm going to go ahead and do that here. I'll put 4t in the front. Now I need to get t by itself. This is 4 times t times the ln of this business. So now I need to divide both sides by 4 times the natural log of 1.07075. What I'm going to be left with, this is going to be what I need to figure out here. Now, you're going to need to put that into the calculator. Let me show you exactly how you'll want to type it into the calculator. You're going to want to do ln of 39,279.16 divided by 37,000. Then you need to divide that by, in parentheses, 4 ln of 1.0075 and close off 2 parentheses. If you type it into the calculator exactly like this, using your ln's, using division properly, notice I put the whole denominator in its own set of parentheses. You should end up with t equals, you should get 2. You might get a little bit of change, but what we're going to do is we're going to round it to the nearest tenth, which will be 2.0, or just 2. Okay, so that one is kind of nasty. Lots of logarithms flying around. If there are any questions on the next exam that involves all this finance business, that formula will be supplied to you. So just keep that in mind if you need. Okay. So now what I want to do with the rest of class is I want to review a few things. Review. So give me a second to pull up the review. And some of the materials I have. Okay. So I'm going to work just a few select review problems. I'm going to work them directly from your review. So the first problem here, we're looking at two functions. We're looking at this thing here and this thing here. And we're asking, are these two functions inverses? Well, they are inverses if they are just reflections about the line y equals x. So looking at a graph, two functions are inverses if they are reflections about the line y equals x, which is this line right here, this dashed line. And so if you look at it carefully, yeah, it looks like one is a reflection about this dashed line. So I'm going to say yes. That's all there is to it on that one. And we'll just look at them and I'll decide what we work. This next one is very simple as well. It's just asking, is this function one-to-one? So remember, here's a little refresher for you. Remember, a relation is a function if it passes the vertical line test. So we can clearly see on this one, this is just review kind of, if I take a vertical line here and I pass it through, it never hits the function more than once. So this is indeed a function. So we have a vertical line test. That's great. We already knew that one. But a function is 1, 2, 1 if it also passes a horizontal line test. That's what we care about in this problem. So I'm going to take a horizontal line and I'm going to move it up and down the entire function. And I'm going to see that, oh yeah, it passes the horizontal line test as well. Because if I cross the horizontal line test through it, it never hits the function more than once. So, yes. This function, though, will clearly not be one-to-one, because if I move the horizontal, I mean, it immediately fails. Look, it's hitting the function at least twice in many, many places. Down here, it's hitting it again. No, this thing is an absolute failure at being one-to-one. And remember, if a function is one-to-one, that means it has an inverse. That was one of our requirements for saying that a function has an inverse. So let's see, we got only so much time. Lots of questions on inverses on this. There's a few facts we can remember. Whenever we're looking at an exponential, let's see if I can make this larger. When we're looking at the graph of an exponential, f of x equals a to the x, remember we argued that the base of the exponent, if it was greater than 1, it would be a rising exponential. But if it's between 0 and 1, it's going to be a falling exponential. And we argued that. We looked at the graphs, or rather we looked at some graphs of different types of exponential equations. Here's a simple one. Let f of x be equal to 2 to the x. Find f of 4 Okay, so f of 4 is going to be just 2 to the 4th, which is just going to be 16. So it's just function notation, which is something you should already be comfortable with. Simple function notation. So we'll look at this one real quick. The graph of f of k equals negative 1/8 raised to the k plus 3 minus 7. This is just a transformations question, which really goes back to chapter 2. And so we don't really care. We don't really care that it's an exponential. It's just look at what's going on. You're adding 3 directly in with the variable. That's going to move it to the left 3 units. You're subtracting 7 from the entire equation. That's going to move it down 7 units. And then you're negating the function itself, not the variable. So that's going to reflect it about the x-axis. So just remember your transformations of functions. This next one's going to be rock simple. G of x is 1/16 to the x, g of 3 halves. So g of 3 halves well, that's going to be, we plug in 3 halves in for x. So that's going to be 1/16 raised to the 3 halves power. One over 16 to the 3 halves power. And now there's 2 ways we can do this, but honestly, you can put this bad boy into your calculator. Exactly as you see it. You can do it like this. 1/16, put that in parentheses. Do the caret key, and then raise it to the 3 halves power. I would put 3 halves into parentheses as well. That's what I would do. And you should end up with 1/64. If you're curious, an alternate way to do it is that the 3 halves power is to first take the square root. The square root of 1/16 is the square root of 1 over the square root of 16, which is 1/4. Then you cube it, you do 1/4 times 1/4 times 1/4. But you can do that, or you can use your calculator, whatever is your fancy. On that one. So we're just working some select problems from the review. That one's pretty easy. Here it wants us to solve this equation. 2 raised to the 12 minus 2x power equals 256. Well, there's a number of things we can do. It looks like this one has a silly little trick. And the little trick is that 256 can actually be expressed as a power of 2. 256 can actually be expressed as a power of 2. But we can do that, or we can rewrite as a logarithm. Which I'm happy to do at this point. That's going to be the log base 2 of 256 equals 12 minus 2x. And then that one's not so bad. We can do the log base 2 of 256. We can actually use our calculators to evaluate that. So we will use calculator. You can use the change of base formula and just tell yourself that's the ln of 256 divided by the ln of 2. Let me figure that one out real quick. You're going to get 8. So now this equation just becomes 8 equals 12 minus 2x. And then that one's, very easy to solve now. There's no logarithms, no exponents, just a simple linear equation. Divide both sides by -2. And you'll end up with x equals 2. So when we would have solved this in section 4.2, we would have used one method, but now that we know logarithms, we can use another method. This one looks bad, except it actually doesn't want us to solve anything or do any real heavy lifting. It just wants us to rewrite this exponential equation in logarithmic form. And so doing so, 11 over 2 would be the base of the logarithm. This 32 over 161,051 business, that's actually going to be the argument of the logarithm, if you remember how to rewrite between exponential and logarithmic form. So it looks like it's going to be this one here. It's going to be, where'd it go? Log with a base of 11 over 2. The argument of the logarithm is the 32 over 161,051, and that's going to be equal to -5. Let's keep on going. I'll find ones that I think are worth really looking at. That one's not that interesting. This one here, solve the given logarithmic equation. There's always some kinds of tricks you can try. I'm going to try rewriting as exponential. I'm going to try rewriting that as an exponential. So that's going to be, the base is 1/3. So that's going to be 1/3 raised to the -3 power is going to be x plus 7. And notice that's not so bad. You have 1/3 to the -3rd, but my variable is not in an exponent or anything. My variable is just over here. It's real easy. You can figure out what 1/3 to the -3 power is going to be. You can even pop that into your calculator. You can pop that straight up into your calculator if you want it as 1/3 caret -3 and hit enter. It's going to give you 27. And so you're just going to be left with 27 equals x plus 7. Subtract both sides. 7 from both sides, you'll get 20. So subtract 7 from both sides, very easy. You're just going to get x equals 20. On that one. And so the last thing we'll do, I mean, these last few problems, these are calculated problems. Log of 0.0001 or whatever it is, you can put that into a calculator. Remember, when it just says log and there's no base written, it's automatically a base of 10. So in your calculator, you can literally type this exactly as you see it. I mean, it's gonna automatically open a parentheses for you. So just close the parentheses off. And you should get, what is that? 1, 2, 3. You should get -4 there is the answer. So the answer will be -4. So these last couple, you can literally, I mean, that's about as lazy as it gets. Log of 7, literally, you can put log of 7, put it in your calculator, and round to 4 decimal points. Here you can use the change of base formula. You can rewrite that as ln of 7 divided by ln of 1/5. And just round to the appropriate number of decimal places. Okay.
Bell rang, so
Y'all have a great day.
did